There's 25, 27, 29, and 31. Ask me any questions. You're finding the indicated term on 25, 27, 29. You're finding the arithmetic sum on 31. And here's 33 and 35. Now let's talk about 35. On 35, it says find 2 plus 4 plus 6 plus 8 plus ... plus 200, the sum of the first 100 positive even integers. Okay, in this formula, you're going to put S sub 100. The n here is going to be the same in here, 100 over 2. Your first term is 2. Now, it's A sub 200, where they were very nice and they gave you the last term there. So you didn't have to go over and find the indicated term, so you just plug 200 there. Does that make sense to you? Okay. Are there any questions on the first page of homework? All right. Here's your second page. We talk about 1 and 3. Number 5, you're finding the 8th term of the geometric sequence, so it's 768. Number 7 is the 12th term, that's negative 10,240. Number 11, you're finding the sum of the first 12 terms of the geometric. It's 531,440. And number 13, the sum of the first 11 terms, 2,049. Are there any questions on that? I need a hand signal. How do you feel on your homework? Good job. All right, today's lesson, guys, we started talking about Pascal's triangle yesterday. Nick, can you read our learning target for today? I can use Pascal's triangle to expand binomials. And we're talking about expanding binomials. What do I mean by expanding binomials, Harrison?
Because at the time I need senior lapsing F through N. The cafeteria corridor.
What do I mean by expanding binomials?
Senior only F through N.
Okay, did y'all hear what Harrison? Harrison, can you say that one more time?
You raise a binomial to like a large power.
So we could raise like x plus 4 to the 8th power. Well, that would take a long time to multiply all that out, wouldn't it? So therefore, you're going to use Pascal's triangle today. You're going to see how we can do that. But before we do that, I want to show you a video about Pascal's triangle. It's a very fascinating triangle. Mr. Hester learned a lot more about it in this video than I did in history and math. I learned some unique things about it when I watched this video. So let me pull this up. I want you to turn around. Watch this.
Open the world of music. It's all here. Get that.
This may look like a neatly arranged stack of numbers, but it's actually a mathematical treasure trove. Indian mathematicians called it the staircase of Mount Meru. In Iran, it's the Khayyam Triangle, and in China, it's Yang Wei's Triangle. To much of the Western world, it's known as Pascal's triangle, after French mathematician Blaise Pascal, which seems a bit unfair since he was clearly late to the party, but he still had a lot to contribute. So what is it about this that has so intrigued mathematicians the world over? In short, it's full of patterns and secrets. First and foremost, there's the pattern that generates it. Start with 1 and imagine invisible zeros on either side of it. Add them together in pairs, and you'll generate the next row. Now do that again, and again. Keep going, and you'll wind up with something like this. Though really Pascal's triangle goes on infinitely. Now, each row corresponds to what's called the coefficients of a binomial expansion of the form x plus y raised to the n. where n is the number of the row, and we start counting from 0. So if you make n equal 2 and expand it, you get x squared plus 2xy plus y squared. The coefficients, or numbers in front of the variables, are the same as the numbers in that row of Pascal's triangle. You'll see the same thing with n equals 3, which expands to this. So the triangle is a quick and easy way to look up all of these coefficients. But there's much more. For example, add up the numbers in each row, and you'll get successive powers of 2. Or, in a given row, treat each number as part of a decimal expansion. In other words, row 2 is 1 times 1 plus 2 times 10 plus 1 times 100. You get 121, which is 11 squared. And take a look at what happens when you do the same thing to row 6. It adds up to 1,771,561, which is 11 to the 6th, and so on. There are also geometric applications.
This is pretty neat
Look
here.
at the diagonals. The first two aren't very interesting. All ones, and then the positive integers, also known as natural numbers. But the numbers in the next diagonal are called the triangular numbers, because if you take that many dots, you can stack them into equilateral triangles. The next diagonal has the tetrahedral numbers, because similarly, you can stack that many spheres into tetrahedra. Or how about this? Shade in all of the odd numbers. It doesn't look like much when the triangle is small, but if you add thousands of rows, you get a fractal known as Sierpinski's triangle. This triangle isn't just a mathematical work of art, it's also quite useful, especially when it comes to probability and calculations in the domain of combinatorics. Say you want to have 5 children, and would like to know the probability of having your dream family of 3 girls and 2 boys. In the binomial expansion, that corresponds to girl plus boy to the 5th power. So we look at the row 5, where the first number corresponds to 5 girls, and the last corresponds to 5 boys. The third number is what we're looking for, 10 out of the sum of all the possibilities in the row, so 10 over 32, or 31.25%. Or if you're randomly picking a 5-player basketball team out of a group of 12 friends, how many possible groups of 5 are there? In combinatoric terms, this problem would be phrased as 12 choose 5, and could be calculated with this formula, or you could just look at the 6th element of row 12 on the triangle and get your answer. The patterns in Pascal's triangle are a testament to the elegantly interwoven fabric of mathematics, and it's still revealing fresh secrets to this day. For example, mathematicians recently discovered a way to expand it to these kinds of polynomials. What might we find next? Well, that's up to you.
Pretty neat, isn't it? A lot that's going on in that triangle.
Now, yesterday we filled out the triangle. So let's look at this. Okay. Now, you filled out the complete one. I helped you get started. Now, in the video, it talked about how each level... Oh, thank you. Forgot to turn the video off. In the video, it talked about how each level... Yes, you need one of those. Okay. How each of those correspond to a power. Okay, and they use x plus y. Okay, so this first level corresponds to 0 power. Because if I raise anything to 0 power, what is that equal to, class? 1. Do you see how that 1 is right there? Does that make sense? The next level, x plus y to the first. Well, that would just be x plus y. What's understood coefficient in front of x and y? 1. That's why you have a 1 and a 1 there, okay? So, if you want to go on and put by each level, that's the power 0. 1, 2, 3, 4, 5, 6, 7, 8. Do that at this time, please. And after you do that, please turn to page 7 in your notebook, and let's look at our examples we have for this. Picking up on number 5, where we left off yesterday. And we want to use Pascal's triangle to expand x plus 2 to the 4th. Traditionally, we would have done x plus 2 times x plus 2 times x plus 2 times x plus 2, but that would take a while. So we're going to use Pascal's triangle to cut down on some time. Alright, so I just need all eyes up here right now. I'll give you time to go back in a minute to write this down, but you need to watch what I'm doing here. Okay. So this is to the 4th power. I find my 4th level right there. You see those numbers. So what I'm going to do is write each of those numbers down. 1, 4, 6, 4, and 1. Okay. So I wrote those numbers down. Are there any questions so far? Okay, now. What you do is you take the first term. That is x. Does everybody see x? You start with that, and you put x with each one of those. Okay, now the power. You start with that power you see there. What power do we have? 4. And you go in descending order with each of those powers, all the way to 0. 4, 3, 2, 1, 0. What's my next term in that parentheses? 2. Instead of going descending order, what do you think we do? Ascending order. So this would be 0, like that, and go back and put a plus in between all of those. So, Mr. Tester, what if one of those is negative? Well, then you're going to see that when you're working the problem. Now, you might say, Mr. Tester, what if that would have been a negative 2? Then you would have put a negative 2 in the parentheses, okay? But it's a positive 2. All right, so let's look at this. Anything raised to 0 is what? 1. 1 times 1 is 1. So my coefficient there is 1. X to the what? 4. So I have x to the 4th. That is 1. That is 1. 1 times that is x to the 4th. I mark it out so I know I've already completed it. Okay. What is 2 to the first? 2. Derek, pay attention, please. 2 to the first is 2. 2 times is what? 8. Positive 8. So I put a plus 8. X to the what? 3rd. Do you see that? I always take care of my coefficient first, okay? Always take care of my coefficient first. Okay? 2 squared. What is 2 squared? 4 times 6 is 24x what? Squared. 2 cubed. Everyone, 2 cubed. 8. 8 times 4 is x. X to the first is x. 2 to the 4th is what? Anything raised to 0 is what? So all this is 1. 2 to the 4th is 16. So 16 times 1 is 16. That is my answer to that problem. X plus 2 to the 4th. Isn't that quicker than multiplying all that out? So you're using Pascal's triangle to expand. Okay, write that down. Number 6 has 2x minus y to the 5th power. So look at Pascal's triangles. What row of numbers would you use? Everybody look at your triangle and tell me. Okay, what are those numbers on there? 1. Very good. It's this row right here. Right here. Okay, so I'm going to write those down. Make sure you leave some room. what term do I go for first? 2x. It's a positive 2x. So I'm going to put 2x here, 2x here, 2x here. Am I descending the power or ascending? So this is going to be to the what right here? Fifth, and then what? And so forth. All the way down to 0. Now my question to you guys is this. Do I put y or do I put negative y? You got to put negative y. So it's going to be negative y to the 0. I'm going to stop there for just a second. Are there any questions on how I set that problem up? Alright, now be careful of that negative y in the problem. I'll show you in just a second. Now, right here, negative y raised to 0 is what? 1. So 1 times 1 is 1. Now, 2 to the 5th. What is 2 to the 5th? 32. So I'm going to have 32x to the what? 5th. Do not forget that x gets that 5 too. So it's 32x to the 5th. Here's where students make the number one mistake right here. What's in front of that y right there? A negative 1. Negative 1 raised to the first power is what? Negative 1. So you have negative 1 times 5 is negative 5. What's 2 to the 4th? 16. So negative 5 times 16 will give you what? Negative what? 80. Students forget to put that negative there because they forgot to look at that negative y. That's going to be negative 80 x to the what? 4th and what? Y. Now here, that negative 1 squared is a positive, so I don't have to worry about that right there, do I? Negative 1 squared is 1. 1 times 10 is 10. 2 cubed is 8. So 10 times 8 is 80. X to the what? 3rd. Y what? Squared. Here I have negative y raised to the 3rd. Would that be positive or negative 1? Negative 1, so you need to keep that in mind. Negative 1 times 10 is negative 10. 2 to the 4th, 4, so what will go right here? Negative 40. X, y what? Cubed. Very good. Here I have negative y to the 4th. A negative 1 raised to 4 power will be what? Positive 1. 1 times 5 is 5. 5 times 2 is 10x y to the 4th. This is raised to 0, so that's 1. 1 times 1. But I have a negative y to the 5th, so that's going to be minus y to the 5th. So my answer to that problem will be 32x to the 5th minus 80x to the 4th y plus 80x cubed y squared minus 40x squared y cubed plus 10x y to the 4th minus y to the 5th. Do you see a pattern in the x? Yes, Tyler?
So the exponents on your final answer are going to match the ones in the expanded.
Well, there's going to be a pattern. You see here, you went from x to 5th, 5, 4, 3, 2, 1, x to the 0. It's just going to have a pattern like that. No y, y to the 1, y to the 2nd, y cubed, y 4th, y 5th. So it'll be a pattern like that. All right, let's look at one more. X squared plus 2y to the 4th. So we're expanding this to the 4th power. So I'm going to go to my Pascal's triangle. Biggest mistake students make sure you count this top row as your 0 power. 0, 1, 2, 3, 4. And I'm going to choose 1, 4, 6, 4, 1. Which one do I start with, x squared or 2y? Parker, please pay attention. Do I descend the powers or ascend at this moment? Descend, that's going to be to the 4th, cubed, squared, 1, 0. Now I go back and get the 2y. 2y to the 0, 2y to the 1st, 2y squared, 2y cubed, and 2y to the 4th.
Students, this time I need seniors. Last name, O through Z. O through Z seniors, go straight.
Anything raised to 0 here is 1. 1 times 1 is 1. That's going to be. How do you handle this? Would you add or multiply the exponents? Multiply. Very good. X to the 8. Mason, make sure you get your homework down there. 2 to the first is 2. 2 times 4 is 8. X to the what? X to the what? 6. What do I put right here? Don't forget about that y. Students forget that sometimes. 2 squared is 4. 4 times 6 is 24. X to the 4th. Y squared. 2 cubed is 8. 8 times 4 is 32. X squared. Y cubed. That's a 3 right there. This is 1. 1 times 1. That's going to be 16. Y to the 4th. There's still a pattern here. I got x to the 8, x to the 6, x to the 4th. It's decreasing by 2. No y squared, y cubed, y4. So there's still a pattern there. Okay. Bell's about to ring, but we're going to continue this tomorrow, practicing this. How do you feel if you feel 80%? Because we're going to spend another day on this practice. I need a hand signal. Okay. All right. Now tonight your homework does do a little bit of this, but we're going to do a lot more practice in class. It's page 10, numbers 2 through 14 even, and 18 through 26 even. You will have a homework check tomorrow, okay? If you have trouble, you can rewatch the video tonight online. If you need to